Hey friends, I want to combine two topics in our lesson today, data abstraction and the doubly linked list. And the reason they work well together is because we're going to talk about combining operations and data together into a single unit. What data abstraction is the separation of a data unit and those operations that work on that data unit. You've worked with this before. You've seen the implementation details hidden away from you. You've worked with integers. Let's just use that as our basic example. An integer, you can add, subtract, multiply it, and you don't need to know any of the details as to how that happens. All you need to know is when you put the integer data type in there, you can do certain things on that data element. The same thing should apply to, or could apply to, almost any data structure that we create. Let's think about the linked list for a second. You've created a singly linked list, and the kinds of operations that you have to do, you have to establish the list, you have to add nodes to the list, possibly delete nodes, and then traverse the list from one end to the other. If we create an ADT or an abstract data type, what we would do is define the struct, the data structure itself, or the payload of that linked list, and then all of the operations that operate on that structure specifically. If we package all those things together, we can provide that linked list to another programmer, and he or she doesn't need to worry about how we implemented the linked list. All she has to do is see or plant that into her program and then just use it. And that's the idea behind data abstraction. An ADT, an abstract data type, is one step removed from object-oriented programming, because what we would do when we move into object coding is take this ADT and create something called a class. Now, the class encapsulates the data structure and then the functions that operate upon that data structure. And then when we want to use, let's say, the linked list class, all we do is instantiate it, create an object of that type, drop it right into our program, and never have to worry about how we add a node, how we traverse the list. We just do it. Now we're going to talk about ADTs and bring into that discussion the idea of a doubly linked list. A doubly linked list is just a list that has an additional pointer attached to it. We could go crazy, really, and have multiply linked lists where there are more than two pointers that organize the list in any way that we want. Let's say we want to store all of our students alphabetically by last name, and then numerically by their student ID, and then by their date of birth, then by their grade point average. We could have a series of pointers that wind all the way through this. But enough of this. Let's go get started and have a look at some code. Data abstraction is a software development practice that ultimately is going to lead you to more effective reuse of the code that you create. In thinking about data abstraction, we're going to come from two familiar points. You have worked with data objects. You're familiar with the built-in and some of the more complex user-defined data types. And of course, you're familiar with creating functions to operate upon those two data types. We can combine those two things together. The idea of abstraction is to separate them, but we can combine them together to create a single unit that is called an abstract data type, or an ADT. This allows us then to package the new item in such a way that we can insert it into other programs that we want to work on. Take, for example, the idea of time. We want to create perhaps a data type called time. Now, time has certain data points. We have hours, minutes, seconds. It depends how deep you want to go with that, but hours, minutes, seconds, and let's say. On those hours, minutes, and seconds, we have a specific set of operations that we perform. We initialize the time to be whatever time it is right now. We increment the seconds, we increment the minutes, we increment the hours. We can reset the time, we can go backwards, we can go forwards and wind forward, we can unwind the clock. We can do any number of things. Beginning programmers would define the data. Then they would define a set of operations on that data and then build the program around that. One of the great things about the ADT is that we can take both those data and operations and combine them together into a single unit so that I can then insert that unit into any program in which I want to use the data type time. When we think about that, we think about one of the first things we learn as programmers, and that is the notion of a black box. When we create an ADT, ideally what we want to be doing is creating it in such a way that the detail is hidden away. It's inside that black box. The data definitions and the way that we operate upon those data definitions is hidden away in that box. Now that's not all that unusual. You have worked with that notion as far as the built-in data types. You've worked with integers, for example. Now, integers you can add, subtract, you can count with them, you can do any number of types of things, but you have no idea how the compiler is handling that underneath the wires there. And we're trying to get to that same idea when we create an ADT. So when we're thinking about that, we're thinking about a new data type that we can just plug in to any program that can utilize that data type. C++ gives us a couple of ways of doing that. There is number one, the method we're going to look at today, which is to create a header file and a compiled library, and then we include that header file, which I'll show you in just a second, but that would essentially bring that data type into visibility within our program. The second method is encapsulation, and that is when we begin to perform this process in object-oriented programming. And so we'll look at that at a later point. So this first example, this first code example, is a single file. And so you see that I define the time data structure at the top. That is my data element. Now all of my operations will enable me to work upon that structure in particular because they know how that structure is formed. And then when I want to use them, I go and bring those items into my, I define a data type of that structure and then call the operations one by one to operate upon that clock. So you can see that down in the code section down here. I define my data element. That'll be my clock. I initialize it by going to new clock. I demonstrate the time, I reset the time, and then show the time again. So it's a very basic, and that's all in one file. Now, C++ enables us to separate separate code. We can take code and we can put parts of code in one file and have, for example, our main and our other functions in another file. We do that through the use of the header file. I could take all of those data definitions and the operations specific to those data definitions. I could put them into a .h file or a header file and then just include that file in my program, and that would look similar to this. You see on the left we have the time adt.h. I have declared my data structure, my time struct. and then the operations upon that structure. When I want to utilize those functions, I can then bring them in by including that entire header file into myprog.cpp. We can go one step further. And this is what you will encounter with a lot of libraries, a lot of commercial libraries. You will get the header file. You will get an object code implementation file which contains all of the functions and the definitions for those functions. And the two combined are then brought into your program file via the include facility. What would happen in the header file is that you would provide a user interface, and that interface would be the prototypes and the documentation for all of your functions, so that your user can see how to properly call and utilize the functions. The actual implementation of those functions can be put into a separate code file, and that separate code file can be compiled in such a way that your user is unable to see the actual code. So you're able to retain the secrecy of your code. You maintain control over that so users can't just copy it and sell it as their own. And then you still have the ability to utilize that. And that would look something like this. So you see that our time ADT file in the upper left-hand corner, I have declared the data structure itself, and then I provided the prototypes for each of the functions that operate upon that data type. Now notice in the time ADT, and I name that file the same as my header file, I include the header file so that as the compiler walks through, he sees his prototypes first, and he understands what he's going to be encountering, and then he finds the actual implementation of that code. And then finally, I do the same thing that I did before. I include time ADT, that provides the interface to the function library, and then it gives me the ability to walk through or utilize all of those functions. So an ADT is not that complicated. I think once you work with it a couple of times, you're going to get the hang of it pretty quick. So when we talk about creating an abstract data type for the linked list, we think about the basic operations that we need, and there are 5 of them. We need to be able to initialize the list, number 1. Check to see if the list is empty or full, so we can quickly determine whether or not there are nodes. This is rather than running through the contents of the list. We want to be able to traverse the list, that is, read from top to bottom, and insert and delete nodes. Other than that, everything we add on beyond that is extra. And so we can package all this up together. We can define our structure and then define those acts that work upon that. Now, as a quick review, the singly linked list, we can do a lot of things with that. We can create lists, stacks, queues, all kinds of useful structures. And remember that we begin with an empty list, and we have a pointer called head, and that head is going to point at this point to null. We place our first node by allocating space, returning the address of that space back to the head node. And so our first memory location is 1010. So we write our data into that, place the payload, and then we write a second item. So notice that the head is pointing to 1010. As I allocate a new node, in this case it's at 1020, what I need to do is link the next pointer up between the two nodes. And so I create a link by passing the address of the new node back to my next pointer of my previous node. And then I can continue on as far as I want to go, simply by making sure that each preceding node has a pointer to the node that follows it. I will always know in a singly linked list that I've reached the end of the list by the fact that the next pointer will equal null. Now, if you need to see the code for this, I'm not going to include it here. This is more of a design discussion, but I will put a link down below the video that will take you back to another video that has a lengthier discussion of the linked list, and it has a lot of code in there that shows you how this is done. Now, when we look at a linked list and we begin to think about how we might modify the ADT, we begin to look at what's different about the nodes. And in a singly linked list, we have to perform two operations. That is, on the very first node of the list, I have to either create a new node and connect it up to the head, or I need to create a new node and connect it up to the preceding list. If I could get rid of one of those operations, it would vastly simplify my code base. And I can do that by adding a dummy node. And so what I would do is put a node in the same structure as the preceding or the succeeding nodes, the rest of the list. But this node exists only to carry the head pointer, or the pointer to the very first node of the list. And that way, once I've done this, you see the 1010 blue or light blue node there. Once I have this light blue node, or this head node, I never again need to check to see if the list is empty, if I have to connect it up, none of those things, because that will always exist. So all I have to do is add nodes, add nodes, add nodes at the end or the front of the list, depending on how I want to do it. So that's one thing I can modify in order to simplify my ADT a little bit. I could also add in the number of elements on the list if I want to have that information handy, and then again I can quickly ascertain the number rather than having to run through or traverse the entire list. So that you can see some usefulness in this way of modifying your linked list. A circular linked list places a pointer to the head node in the very last node. Normally we traverse a list from beginning to end. We know that we're at the end when we encounter the null pointer. In a circularly linked list, I want to be able to go backwards and start over at the beginning of the list. So what I would do is place a pointer to the head node in the very last node of the list, and then every time I add a node on, I would make sure that I would continue that forward. What this does is create a circle, and this is especially useful design-wise when you are working with something that needs to perhaps start an operation in the beginning of the list and then go back and restart at the beginning. So if you have an operation similar to that, this is a quick way of doing this. Rather than resetting everything, you can simply just go back to the head node and start the operation over. When we talk about singly linked lists, we remember that they can only be traversed in a single direction. But if we add one small change to it, we find that we can traverse the list in two different directions. So a doubly linked list, and making this modification is very simple. Where we have a next pointer, we add a previous pointer. So the next pointer would point to the one that follows. The previous pointer points to that which precedes it. So if we look at this, we once again start with a null list, and we add on our first node. Now note that both of those pointers, the preceding and the next, are set to null. This tells me that there is no node before this and there is no node after this. As soon as I add my second node, then we've got to do some assignment of pointers. And so what we'll do is first, from the singly linked list, we will point the next pointer forward so that he has the address to the succeeding node. And we will set the new node's preceding pointer back to the preceding node. And so in this way, I can read from 1010 to 1020. I could also read from 1020 up to 1010. Now you notice that 1020 next has a null pointer, and that would tell me that I've reached the end of the list. And the 1010 back pointer is null, and that tells me that I have reached the beginning of the list. And I can just continue on like this. Now, if you think about this structure, this is really kind of cool, because we could go down, let's say 1030 is the middle of the list, and there are a bunch of nodes that follow after this. We could actually turn around now and walk back up the list. So this double linking gives me the ability to traverse the list in two different ways. Once I have done that, I have one further option that I could add into the ADT, and that would be a pointer to the tail. So if I had an application that wanted to start from both the beginning and the end of the list, if I had a pointer to the tail, I could simply go to the last element in the list and then follow the back pointers to traverse the list backwards. So we have a lot of flexibility now built into the list by adding just one more pointer into the node. We can go one step further with a multiply linked list, and that is a pointer or a node that contains more than two pointers. And when I do this, when we have something like this, this allows me to create a number of paths through the same list. Let's say I have a node called student data, contains a bunch of information about my students. I could then have a pointer to the next alphabetical name in the list. And so I could quickly traverse my list alphabetically. I could add a pointer to the next zip code. So I could traverse numerically from area to area. The class from this to the next to the next. You can do this forever. Now, the more pointers you add, of course, the more complexity there is in your code. But if we are thinking seriously about creating an abstract data type, the user will be insulated from this complexity, because once we give them the ADT and tell them how it is to be implemented, they don't need to worry about the code that links all the things up together. So we have a lot of flexibility by using ADTs, and our goal is to simplify and to be able to reuse these data structures that we create.
Who's got more heart than you? No one!